Hi, my name is Shad, and I'm going to be your teacher and guide today for this course on software reverse engineering. So that's the technique of taking code that's already been compiled and reversing it into something that you can manipulate. So that means you might see the source code, or at least you will be able to see the assembly language and then make any modifications or understanding of what the program is doing. So this course is taught in 8 pieces. In part 1, we'll talk about numbering systems. So if you have not seen binary numbers or hexadecimal before, this will give you a great start into how you can understand what a reversed piece of software looks like. Then we'll do some experiences to get you used to the idea of software reverse engineering, the first attempts. Then we'll have a session where we compare the different tools that are popularly available. And of course, we're looking for free tools, but there are commercial ones as well. And then we'll talk about the reading the stack feature. So this is understanding a program as it's running and doing some debugging while it's in action. Binary patching is about taking a piece of software and modifying it, even if you don't have the source code. And so you can patch things to fix errors or to maybe bypass a certain feature like a login screen or a registration screen. And that's this video here right now. Recognizing code patterns will give you a more in-depth advanced feature of how you can see maybe malware and diagnose what it's doing. And then anti-debugging techniques is the ability to take a piece of software who is trying to hide from you. So this is a cybersecurity topic where we are looking at software that knows that you are reverse engineering it and you're trying to avoid that. And then finally, we'll do some fuzzing techniques. So this whole course here is about software reverse engineering. Now, the guides that are going to take us through here are from Dakota State University. So Michael Ham and Andrew Kramer are both the teachers. So let's get started with this section right now on software reverse engineering.
I'm going to see if I can do a little binary patching and dynamic binary manipulation demo here. And I'm hoping this is something that we can all kind of do together, you can follow along with. So I'm going to put some code up on the screen. We're going to type this up together. It'll just be like 5 or 6 lines, and then we'll throw it in GDB, and we'll see if we can manipulate the code to bypass a check. So let's start out by just creating a little C file here. I like to use Nano because I'm kind of a noob, but if you like VI or something else, that's even better. Awesome. So I'm just going to type this up and then we'll talk about what it's doing in case it's not clear to anybody, but go ahead and follow along and type this in as well. And we'll say else, if it wasn't equal to a random number, then printf invalid key. And that's everything right there. So up at the top, I have 2 include statements. The first, standard IO, that stands for standard input output. That's like our print and our scan functions for input and output to and from the user. And the second include, standard lib, standard library, is going to give us this rand function. Rand just generates a random number, right? So when the program starts, it's going to ask us to enter a product key, like many programs would. And then it's going to read a number from the user. So we'll type in like 1, 2, 3, 4. And then it's going to check to see if the key that we entered is equal to a random number. Now, just a point of note here. For some reason in Kali, they like make the 2 equal signs 1 equal sign. I know that looks like 1 equal sign. Make sure that is 2 equal signs. Is that clear? I think that should be obvious, but yeah, I don't know why it does that. I don't like that. That's 2 equal signs. So we're going to say if the key that the user entered is equal to a random number, which should be quite impossible for us to predict, unless we run this 4.2 billion times and you get really, really lucky. If we get the random number, it's going to tell us welcome to the full version of the product. Otherwise, it's going to tell us invalid key. Okay, cool. So let's compile this code. And what we're going to try and do is use a couple of methods to bypass this check to get us the full version of the product without entering the correct key. I'm not encouraging any illegal activity here, but it's just a fun example, you know. Okay, so I'm going to close this file. And I'm going to compile this, gcc example.c, and just to keep things simple and consistent, I'm going to compile it 32-bit. So I added a -m32 to the compilation line there. And if you want to change the output name, you can use -o. We could say like example.out, or if you just leave that -o parameter off, it will just be called a.out. So I'm going to hit enter. And if we see nothing, is that good or bad? That's good. Yeah, generally in like Linux and Unix, no output is good. But if I look in my folder here, I should see a new file called a.out. That is my program. And assuming that I wrote that program correctly, when I run this, it should ask me for a product key. I'm going to enter a number, 1, 2, 3, 4. And if this says welcome to the full version of the product, then we're canceling class right now and I'm going to the casino floor and I'm going to drop all the money in my pocket, which isn't much to begin with. So, invalid key. Okay. Anybody by chance get welcome to the full version of the product? I'm guessing not. Okay, cool. So, let's say that we would like to have the full version of the product without having to get the right key. Or maybe this is a piece of malware and it's doing some specific check and I don't want to have to worry about what it's actually checking. I just want it to reach a different place in the code and start executing that portion of the binary. Right, this could be for legitimate purpose as well. What can we do to bypass that? So I'm going to show you two methods here. I'm going to show you one method that works just dynamically in the moment while we're debugging the program. And then we're going to open up a hex editor and we're going to try and make a little change to the binary that will make that permanent so that we get the correct answer all the time. That's our goal. So let's go ahead and start this program in GDB. So I'm going to do GDB a.out. And I have Jeff installed here. You all do as well now. Let me see if I can shrink this window just a little bit so you can see the whole thing. Okay, so if I just run this program without any breakpoints, it's going to go ahead and start, ask me for the key, I enter a key, it exits, nothing interesting happened. I would like to get the program to pause somewhere around the point where it's performing that check. Anybody want to suggest an idea, a command, a couple of commands, or just an idea for how I could pause the program at just that location? What would you do here? I'm going to pause right before the check. Breakpoints, yeah. How should I figure out where to put a breakpoint? Whoops. Yeah, so let's disassemble. Disassemble. You have to spell it right. Disassemble main. Let's just disassemble the main function. Now, I'm making some assumptions here. If this was a real piece of malware, I probably would have opened it in IDA first and looked at which function I want to disassemble and found the address, and there would be some more steps involved. We're just assuming that only main is the only function being used here. So we'll disassemble main. There it is. And this will be a fun exercise. I'm just going to let you kind of look through here. And when you're ready, somebody raise a hand and see if you can tell me on what memory address, what pointer within this main function does the comparison between the random integer and the key that I entered take place.
77?
Yeah, so it looks like main plus 77 here, which is the memory address 56, 55, 62, 1A, that's going to be our compare EAX, EDX. So where did EAX and EDX come from? Let's look backwards in the code, and it looks like, let's see, EDX came from the D word at EBP minus C. We know from what Mike just did that EBP minus C is probably a local variable. And in fact, if I look up a little bit further, I should see that that was used as an argument to scanf, right? When I call scanf, EBP minus C was my key variable. And then I don't see EAX being set anywhere. Can anybody tell me where or how EAX is getting set? Yeah. Remember, EAX is always the return value, or that's where a return value is stored. So because I called rand just before this instruction, EAX is coming from rand. So it looks to me like EDX from this local variable and EAX from rand are being compared here, and if they are not equal, then we're jumping down to main plus 101, otherwise we continue on here. So this is kind of our if-else statement. And we're looking at it in linear disassembly, but you know, we could open this up in IDA and see a nice control flow graph with two options. So if I don't want to actually modify this binary at all, inside of GDB, while this program is running, I could put a breakpoint right here on this compare, and then before it goes to the next instruction and executes this jump not equal, I can just manipulate these values to lie to it, right? It doesn't matter what rand gave me or what number I input. If I can just change these registers right here before the comparison happens, I can force it to do something else. So I'm going to put a breakpoint right on this instruction. The way that I like to do this is take the memory address. This is a little bit different from what Mike did, but both are equally valid. I'm going to copy that, and then I like to say break star and give the pointer there. Now that I think about it, maybe I like Mike's method better because you get the function name. I don't know. It works either way, right? So I'm just going to say break star and then that pointer. And then I'm going to go ahead and run the program. I know that the program is going to pause right there where that comparison takes place. So I can run it. It's going to ask me for a number. I can enter a number. Let's enter 1, 2, 3, 4. Okay, some extra 4s. My keyboard key got a little sticky there, I think. Okay, and there we go. We hit our breakpoint. Now, I'm going to zoom out just a little bit. I want to keep this large enough that you can see, but I want to get more on the screen here at once. Is that still large enough that everybody can see? I can zoom in a little bit if not. So, what do we have here? So I have a breakpoint on compare EAX, EDX. EDX is 12D60C, and EAX is 6B, 8B, 45, 67. Now I could probably convert those to decimal and figure out what number I should have entered, but it's going to change each time, right? Let's just do this. Let's set both EAX and EDX to 0. Then I don't even have to think about what those numbers are, and then they're guaranteed to be the same, right? So before I go any further with the program, before I let it continue, I'm paused here on the compare, I'm going to say set $EAX equals 0. That syntax can be a little bit weird the first time you see it. $sign in front of the registers, equal sign, and then a number. And then I'm going to do the same thing, set EDX equals 0 as well. So I'm overwriting the random number, the return value, as well as the key that I entered, both with 0. And then here's a nice trick. Actually, Mike showed us this as well. If you just type context or CTX, it will show you again the new state of the registers and RAM without actually running any further. So I set both registers to 0, run context, and what I'm hoping to see here is that EAX and EDX are now equal. So I have EAX equals 0, EDX equals 0. This comparison should now be true, right? So, when you're ready, go ahead and type, what should I type to let the program keep going? C, yeah, or continue if you want to write the whole thing. C or continue. And when the program continues running, congratulations, we now have the full version of the product, right? And so again, this same principle can apply in malware analysis or any other reverse engineering task where you just want the program to reach some specific point, and you don't want to have to worry about debugging or reverse engineering a complex function to figure out what input you need or should be there. You just want to get to that next point. This trick can let you do that. Okay, so I think it would be fun then to take this a step further. Obviously, I've proved that I can make the program do something different while it's running inside the debugger. But wouldn't it be great if I could patch this program so that that happens every time, right? I want that to happen every single time. So, what I need to do, well, I'll turn this over to you all. How do you think you would approach this problem if you were going to try to change the binary in some small way, make a very small change, such that every time I run it, even outside of the debugger, I always get the full version of the product? Any ideas here? Bailey. Yeah. Yeah, so check it out. This comparison and the jump that follows it says if we entered the same number that Rand just gave us, continue on, but if they were not equal, I want to jump to a different place in the code. So what if I just invert this condition? What if instead of a JNE here, I make a very small change to the program's code, the actual like hex bytes in the binary, such that instead of a JNE, it performs a JE. So if and only if I guess the random number, will it tell me that the product key is invalid. But for any other number, 4.2 billion minus 1 out of 4.2 billion, I get a valid product, right?
We could just compare the same register to itself.
That's true. That's another way, right? So there are countless ways that we could manipulate this program to achieve this. That's another good example. What if I change this comparison so that instead of comparing EAX to EDX, it just compared EAX to EAX? Or here's a good one. Are you all...
Some knobs.
What's that?
Throw in some knobs.
Yeah. Do you all know what the NOP instruction does? 0x90, do nothing, no operation. Assuming that the flags that compare would have set are already set in my favor, what I want them to be, that's a if, I need to think about that. We could just knock out this comparison and then the jump will not jump down. So there's a lot of different ways that we could accomplish this, and depending on how we want to modify the binary, we could use any one of them. I'm going to stick with just switching the jump not equal for a jump equal, because I tested that a few minutes ago and I know that it worked. And then my demo won't blow up and fail here. So what we need to do is we need to figure out where in the binary those bytes that we need to change are. So, should we use Radar 2 for this? Let's do that. Let's do that. So I'm going to quit out of GDB. And let's start R2 against the a.out file. The -w flag makes it writable, right? I can change the program as I'm working with it. You know what? I actually don't know how to change a byte from Radar 2. I did it in a hex editor earlier. I'm going to let you teach me that in just a minute. Okay, so we're going to open it in R2 with -w. That's important. And I'm going to go ahead and analyze this. We'll give it, I don't know, 3 or 4 A's. Just perform some basic analysis. And I want to seek to the main function and then print the disassembly for that main function. So does anyone remember what the command in R2 was for seek? It was just a single letter. I didn't want S. Yeah, S is a good S. So I'm going to seek to symbol.main, and check it out, that tab completes. Love it. Makes your life so much easier. I'm going to seek to the main function, and then I'm going to print the disassembly of this function. I think that's what that stands for. PDF. PDF is the command that will give you the disassembly of the current function that you're at. I think that we also could have typed PDF at symbol.main, maybe. I think that also works. So here I have the function, and it looks like that right there is my comparison. That's the one that we were looking at initially, right? So I suppose now what I need to do is seek my file pointer down to that level and then modify one of these bytes. I'm going to actually modify the jump, right? So I did this in a hex editor earlier, but I'll let you, what commands would you run to seek the pointer to here and then modify this?
Do you want to do it the even easier way visual though?
Yeah, let's do it, okay.
All right. So do the one capital V.
Okay, so do a single capital V. Oh, brilliant, because it has a hex editor here. Brilliant. So just type single capital V and hit enter. And I'm going to note this address as well. The address that I'm going to seek to is 121C. Yours might be different depending on if you had any extra code in there that I didn't. Probably should be.
Yeah, you can seek there first.
Oh, okay, so I could do like seek to 0x121C. Will that work? Yeah, look at that. Okay. So now our file pointer has like moved to that point in the binary. Now when I do capital V, I'm looking for these bytes 7514. That's what I'm hoping to see when I enter visual mode. There we go, yeah. So I can see my pointer right at the top there is at 121C, and I have 7514 as the opcodes for that particular instruction. Now before I actually change this, let me show you a really cool online tool that will make your life easier if you haven't already found this. If you open up a web browser and you just search for online assembler, the very first link is to this defuse.ca online x86 assembler. I would love to meet and shake the hand of the person that made this tool because it's amazing. It's so nice. Basically, we can type in instructions like JNE. Oh, this might be more complicated than I thought. Uh-oh.
Yeah, because you have to change it.
Let me see if, okay, hold on. What's that? Oh, does it? Okay, show me how to do it with R2.
It's part of the tool set, so if you open up, you do it in here, but if you open another window, and just it's called RASM, R-A-S-M-2.
Oh, yes, of course.
Yeah, that's good.
Brilliant. Can I just pass it like
Yeah.
JNE dollar plus some number? Look at that. Awesome. Okay, so let me back up a moment and talk through what just happened, because we just tried a lot of things. So, one thing that I wanted to show you here is that this online tool is awesome for converting between assembly and opcodes, or vice versa. So if I take an instruction like JNE dollar plus 14, and I click a symbol, that's going to give me 7512, which is a jump if not equal the current location plus 14. I can also do that in reverse. So if I was to put 7512 here, that is jump if not equal, gives me the same thing back out, right? So this is a nice little online utility for quickly converting between one and the other. But what I just learned, I love this, is that there is RASM2, RASM2, which you can pass an assembly instruction as its first command line argument, and it will give you the bytes for that thing. So what I'm going to do here is just change that first instruction. Now, the offset is not the same as from the binary. I'm not really worried about that. I just want to see how this first byte is going to change in order to make it a, that's not right, a JE instead of a JNE. So when I run that, what changed? Yeah, so instead of a 75, Now I have a 74. That's it. 1 bit, literally, changed between the two. So back in my hex editor here, in R2, can I just start typing to
So you hit C.
C? Okay, so C allows you to edit.
C to get the cursor over where you want to edit. There you go.
Nice.
And then I to insert X. And now you can put the X that you want.
Brilliant. So one more time, that was C to put the cursor in the hex window. And then I for insert mode. And then I just typed 74 instead of 75. And what I'm hoping, since we were in write mode, we changed that, I'm hoping I can save the binary, and now every time that I run it, well, every time except 1 out of 4.2 billion, approximately, it should give me correct product key. Okay, so what do I need to do to... Oh, so it's like Vim bindings, kind of? Okay, so Q to quit out. And then I assume Control
Q again.
Q one more time. So QQ. And then do I need to do like
Q to exit, yeah.
QW or just Q? So 3 Qs and then an enter. So we used a C to move the cursor, I for insert mode, type your hex byte, and then just quit, 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 and we should be back here. So before I run this, I'm going to just take a look at it in R2 one more time, and I want to take a look at that instruction and see if it's changed. So I'm going to analyze it again, AAA, and then I'm going to seek to symbol.main, and then I'm going to print the disassembly of that function. So I opened it in R2, analyzed it, 3 A's, seek to symbol.main, and I'm going to print it out again, PDF. And I want to see if that instruction now says JE. I guess I could have just run the binary to check, but look at that. So we've changed it from a JNE to a JE. So let's quit back out. And could I get a drum roll, please? Okay, here we go. And, oh wait, I have to do this also. And we have the full version of the product. Hallelujah. So there's a couple of different ways, both one time in the moment in a debugger and permanently for as long as you want to work with the binary, to make it do something different depending on where you want the control flow to go. Now, you can extrapolate this concept out to anything, right? It doesn't have to be a jump that we're changing. You could change values that get saved in memory. You could knock out checks that are like checking for a debugger. Maybe there's going to be a CTF challenge on that in 1010. You could knock things out. There's a variety of different ways that you could use this to influence what the binary does. So I think that's kind of cool and interesting. Let me show you one other way that we could have done that. This is another tool that I discovered just earlier. Kali has this tool called Hex Editor. I've always used one called Hex Curse in the past, but I really like this one too. Hex Editor. Did you all know this exists on the command line here? Man, learn a new thing every day. All right, I'm just behind. So if we opened up a.out in the Hex Editor on Kali, this is another way that we could have accomplished that. While we're here,
what kind of interesting ways can programs prevent that?
Prevent that from happening? So, thinking from a defensive perspective, I mean, it's really hard, right? Because ultimately, the person running the code has the binary, and they can do whatever they want. So one idea is, maybe you could put some code up at the top that hashes the whole file, hashes itself, and then refuses to run if the hash is wrong. How do you bypass that? Yeah, you just, right? You just knock out the check for the hash. Or maybe you have, oh, I don't even know. I mean, you could get creative, I guess. Yeah, obfuscate, just make it harder to find, harder to get at. But ultimately, the reverse engineer, the person working on the code, has all of the code in front of them. They can change it any way they want. They can modify it any way they want. I mean, heck, if there's a mile of barriers in the way of me executing the function that I want to run, maybe I just change the entry point of the binary to point to that function and just skip over everything, right? That's hard. I don't know that I have a good answer for that. That's a really good question. You know who you could ask about that is game developers, because they have worked very, very hard to prevent reverse engineering.
But they still good.
Yeah,
Shit,
it's-
right? You can still get cheat several.
Yep. It's a cat and mouse game, and the reverse engineer always wins. In the end, with enough time.
What I mean, like you said, in principle, that reverse engineer has the code.
Yep. I like to say all code is open source if you know assembly, and then just work from there.